In a world where beautiful glass buildings exist, where techniques of implementing this material are constantly being improved and new methods of application are being developed, glass is being used more and more in all kinds of structures in order to make full usage of its transparency and aesthetics. But beauty has a price, and beautiful things should be protected. Glass buildings are exposed to the sun, and with the current market, there is no protection for multidirectional bent glass structures. These buildings are either exposed to a higher chance of overheating, which results in more usage of cooling energy, or they simply have to sacrifice their aesthetic appearance by reducing the transparency or by changing the color. Fear not, we as camping crew have the solution. We have made Parshade. We have created a system that is invisible, that is aesthetically pleasing, that is quick, and is also adaptive to any shape of glass, but also isolates. We have made Parshade. But how does this work? Parshade has been developed through taking a standard point hollowed glass system with a steel construction behind it. By hollowing out the connections, room is made for particles. Particles would flow to the cavity using compression. With suction, the particles will go back to its storage, that is located inside the building structure. As you can see, there are no visible parts around the glass. The main part of the system can be centralized in your basement. The vacuum and compressors can be located here. And how does this look in practice? Parshade is an exemplary product for buildings with complex multi-directional bent glass facades, such as the one seen here. Every glass pane can be filled individually in order to only provide sun shading where it's necessary. For buildings with large glass facades, this can also be used to create interactive patterns which the neighboring street can enjoy. From the inside, the system looks like this. A sunshade system that never closed in exactly the same way. A system that is truly something you actually want to close and open over and over, just to have another look at it. And how did we even come up with this? We translated the real case scenario to a wooden prototype that we could make ourselves. We started off with researching possible cavity fillers in order to ensure that there was no outer system required in order to sunshade the complicated shaped glass. We tested different kinds of transport tubes and flow patterns. With highly accurate machined parts, a connection was made between the storage and the cavity. To show off the capabilities of the system, a 3D shaped glass panel is recreated. With some coating, gluing, and vacuum forming, this was recreated. All there was left to do was assembling. After some successful tests, but also some failures, we got a working prototype. As you probably would have seen at this point, this product shows some great potential, but we are not there yet. Although the prototype was working, it was not consistent. Air leakages appeared frequently and particles would just blow out all over the floor. The used vacuum did not have enough power to lift the particles up the 40 cm high panel, so we need to think of what we will need to use for a 3 meter high case. We also had to deal with static electricity that would build up in the system and the glass would deform under the vacuum. But we are proud to deliver you Parshade. During the building weeks, we discovered quite a few problems, as was discussed before. We also discovered that by changing the position of the vacuum inlet and by rotating the reservoirs into a horizontal position, a lot of these problems could potentially be solved. The most important problem we came across is the fact that the cavity of the glass doesn't completely fill, because gravity is preventing some of the particles from being pushed out of the reservoir. The goal is to optimize this filling process to achieve a cavity that is completely filled as shown in the schematic. To achieve this, a test setup is made. Several reservoirs are made, each with different locations of the vacuum inlet. In this subdivision, a distinction is made whether the reservoir is going to be placed vertical or horizontal. As a next step, a camera is set up in front of the prototype. By putting a black screen behind the glass pane, a starker contrast is created between the background and the white particles. For every picture, equal amounts of light will be shining around the prototype. Then, by pixelating every image in the same way and turning them into grayscale, good comparisons can be made. After this setup process, it is time to run the tests. Every variant is run 10 times. After each run, a picture is taken, pixelated, turned into grayscale, and appropriately named. These pictures are then evaluated based on how many pixels have a white color, defined as ranging from 200 to 255 on the grayscale range. With the average value of each test, conclusions can be drawn about the best vacuum inlet position and orientation of the system. The picture with the highest amount of white pixels will show which variant is the most optimized.